Pluto, a far-off and mysterious planet, was once viewed as a component of our neighborhood planetary framework. However, recent groundbreaking statements by leading astrophysicists Neil deGrasse Tyson and Michio Kaku have pushed Pluto back into the spotlight. They suggested that this frigid world may be on a potential impact course with Neptune. How might this be within the realm of possibility, and what results would such a devastating event have? Could this be a captivating cosmic phenomenon, or is there something else to this approaching disaster? Join us as we delve into the potential consequences of a Pluto-Neptune collision. Once classified as a planet and later reclassified as a dwarf planet, Pluto remains a subject of fascination in the vast universe. This is evident from recent theories by renowned experts. Pluto's orbit closely intersects with Neptune's, raising concerns among astrophysicists, including Neil deGrasse Tyson and Michio Kaku, who warn of a potentially catastrophic collision between the two, with significant repercussions for Earth. But how could such an event occur? Pluto's journey around the Sun is unlike that of any other planet in our solar system. It takes a staggering 248 years to complete a single orbit. Since its discovery in 1930, Pluto has not yet completed a full revolution. The intrigue doesn't end there. Pluto's orbit is highly elliptical, deviating significantly from the nearly circular orbits of the major planets. A particularly fascinating feature is its tilt, 17 degrees to the ecliptic plane, making its path noticeably skewed compared to other planets. This inclination and eccentricity introduce additional layers of complexity to its orbit. One of the most remarkable aspects of Pluto's orbit is how it intersects with Neptune's. For about 20 years during each orbit, Pluto moves closer to the Sun than Neptune, contradicting what one might expect based on their positions in the solar system. This raises a natural question: why hasn't Pluto collided with Neptune? The answer lies in the gravitational interactions of various planets. The study of Pluto's orbit began after its discovery as astronomers sought to understand its unique path. Unlike most planets, whose orbits lie close to the ecliptic plane, Pluto's orbit stands out due to its steep inclination and unusual shape. The mystery deepened as scientists realized that Pluto's orbit actually crosses Neptune's. Despite these complexities, the stability of Pluto's orbit highlights the intricacies of celestial mechanics. The three-body problem in space refers to the challenge of calculating how three objects, like Pluto, Neptune, and the Sun, interact gravitationally. This is akin to predicting how objects will move based on their initial positions and mutual gravitational influences. In Pluto's case, this problem demonstrates how its orbit, Neptune's, and the Sun's gravity all interact in a complex manner. Astrophysicists use terms like non-concurrent libration, orbital precession, and the VZK oscillation to explain this phenomenon. Non-concurrent libration refers to the fact that whenever Pluto crosses Neptune's orbit, it is at least 90 degrees away from Neptune. This spatial separation is crucial in preventing a collision. Orbital precession describes the slight vertical movement of an orbiting body. For Pluto, this means that when it approaches Neptune or another massive planet, it is positioned above their orbital plane, adding another layer of protection. VZK oscillation describes how Pluto, Neptune, and the Sun's gravitational forces influence each other. This oscillation helps maintain Pluto's orbit, preventing erratic movements that could lead to a collision. Despite Pluto's seemingly irregular path, this oscillation stabilizes its motion over long periods, revealing that even chaotic-seeming systems follow hidden patterns and rules. These factors help keep Pluto's orbit stable, ensuring that it does not crash into Neptune or drift too far off its course. The three-body problem is crucial for understanding changes in these orbits and the interactions between celestial bodies. Studying this helps scientists learn more about Pluto, our solar system, and even distant stars and planets. Mathematical simulations during the 1980s revealed that, despite these stabilizing effects, Pluto's orbit is unpredictable. Even small variations in its initial conditions could lead to significant changes over centuries. Nevertheless, Pluto's orbit has been found to maintain stability over extremely long time scales. Further studies have helped us understand how Neptune, Jupiter, and Saturn influence Pluto's orbit. There is a remarkable relationship between Neptune and Pluto. For every 2 orbits Pluto completes around the Sun, Neptune completes 3. This relationship helps keep Pluto's orbit stable. Jupiter's immense gravity also plays a crucial role in stabilizing Pluto's orbit, preventing it from straying too far into Neptune's domain. Saturn's gravitational pull adds another layer of stability. These findings suggest that Jupiter, Saturn, and Neptune work together to ensure Pluto's safe passage through space without encountering significant disruptions. Without these gravitational interactions, the solar system could be a much more chaotic place, where objects like Pluto might collide with other planets or be ejected from their orbits, triggering a chain reaction of events. Understanding Pluto's orbit is essential, especially when discussing the possibility of it colliding with Neptune in the future. It also gives us a clearer understanding of the dynamic nature of our solar system. The case of Pluto illustrates how even the most seemingly unstable orbits can reach a state of equilibrium through the intricate interplay of gravitational forces and orbital mechanics. It also highlights the importance of continuous observation and research to better understand our place in the universe. The study of celestial bodies often leads us to confront their bizarre behaviors, and Pluto's orbit is a prime example of this strange nature. The concept of orbital chaos, which refers to the sensitivity of a celestial body's orbit to its initial conditions, is clearly demonstrated by Pluto's path. Even slight changes in its position or velocity can lead to dramatic shifts in its long-term orbit. Digital simulations have been instrumental in helping researchers understand Pluto's movements in space. These simulations use advanced mathematics to model the gravitational interactions between Pluto, Neptune, and other bodies in the solar system. By adjusting small details in the simulations, scientists can observe how even tiny shifts can significantly alter Pluto's trajectory. In the late 1980s, these simulations revealed fascinating insights about Pluto's orbit. While stabilizing factors like non-concurrent libration and orbital precession help maintain stability, Pluto's orbit can still be unpredictable if its initial conditions vary even slightly. However, despite its apparent chaos, Pluto's orbit remains stable over vast timescales, billions of years. This suggests that, despite the seeming randomness of Pluto's journey around the Sun, there is an underlying order to it. Predicting the movements of celestial bodies, especially those with irregular orbits like Pluto, is an enormous challenge. The inherent unpredictability of these systems means that long-term forecasts are fraught with uncertainties. While mathematical models are invaluable in understanding and predicting the future movements of celestial bodies, they also highlight. While we have gained unimaginable headway in understanding space, Pluto's case exhibits how much there is still to discover. The gravitational impacts of the giant planets on Pluto's orbit provide important insights into the broader workings of the planetary system. They reveal how the positioning of each planet can significantly affect the stability and trajectory of various bodies within the system. So why have prominent astrophysicists recently raised concerns about a potential collision between Pluto and Neptune, despite all these forces working to keep them apart? Neil deGrasse Tyson, a leading astrophysicist, offers a unique perspective on the mysteries of our solar system, particularly Pluto. Tyson, who played a role in Pluto's reclassification as a dwarf planet, provides valuable insights into the evolving understanding of celestial mechanics and the public's renewed interest in overlooked aspects of space. He sees Pluto's reclassification not as a demotion but as a necessary change based on the expanding knowledge of the various objects orbiting the Sun. He believes that the complexities of orbits like Pluto's reflect how much is still left to explore in space. The ongoing fascination with these questions fuels the excitement of space exploration. Despite Tyson's optimism, his concerns about a possible Pluto-Neptune collision suggest that there are still many uncertainties regarding Pluto's orbit. Will Pluto crash into Neptune, or is this just another instance of confusion in our ever-changing universe? Only time and further research will provide an answer. For now, we are left with a heightened curiosity about how little we actually know about our own solar system. We continue to study these celestial phenomena, aiming to uncover the secrets that lie beyond. The possibility of a Pluto-Neptune impact raises further questions about the mysterious and captivating universe in which we exist. The idea of a collision between Pluto and Neptune challenges our traditional understanding of planetary stability, particularly given the current relative stability of their orbits. Considering Pluto's position at the outer edges of the solar system, far from the major planets, and Neptune's status as a gas giant with a strong gravitational field, the implications of such an impact would be significant for our understanding of gravitational interactions and solar system evolution. To comprehend the dynamics of a potential collision, one must first consider the composition and properties of Pluto and Neptune. Pluto, despite being a dwarf planet, is composed of various substances believed to exist in a frozen state due to the extreme cold of the outer solar system. Its surface is covered with nitrogen ice, and its atmosphere consists mainly of nitrogen, methane, and carbon monoxide. In contrast, Neptune, a massive gas planet, is primarily made of hydrogen, helium, and other lighter elements, with a dense, deep atmosphere. A collision between these vastly different bodies would significantly alter their structure and behavior, potentially creating an event visible across vast distances. What makes this hypothetical impact particularly fascinating is the influence of other bodies in the solar system. While Neptune's gravity plays a key role in stabilizing Pluto's orbit, it is not the only factor at play. Jupiter, with its immense mass and strong gravitational pull, also has a stabilizing effect on Pluto's orbit, preventing it from drifting too close to Neptune. Saturn's gravitational influence further complicates the dynamics of the outer solar system, making a catastrophic event between Pluto and Neptune highly unlikely. Despite the apparent risks, ongoing research has shown that the relationship between Pluto and Neptune is far more complex than a simple collision course. The gravitational resonance between Pluto and Neptune, where, for every 2 orbits Pluto completes around the Sun, Neptune completes 3, creates a cosmic lock that prevents them from directly colliding. This resonance is a crucial factor in ensuring that Pluto and Neptune's orbits, while they cross in space, have never resulted in a direct impact. As we continue to explore the relationship between Pluto and Neptune, it is essential to understand the broader context of solar system stability. The forces at play in this delicate cosmic balance extend far beyond the interactions between Pluto and Neptune. For instance, the influence of the Kuiper Belt, a region filled with icy bodies located beyond Neptune, also plays a significant role in shaping the orbits of distant objects like Pluto. The Kuiper Belt serves as a boundary zone for many dwarf planets, comets, and other small celestial bodies orbiting the Sun. These objects, including Pluto, frequently interact with the gravitational forces of the giant outer planets like Neptune, contributing to the long-term stability of their orbits. Pluto's orbit is not only affected by the gravitational forces of Neptune, Jupiter, and Saturn, but also by the movement of other objects in the outer solar system. The gravity of distant objects, including the vast number of trans-Neptunian objects, can occasionally shift Pluto's orbit in subtle ways. However, these shifts are typically minor enough that they do not disrupt the overall stability of Pluto's path around the Sun. Interestingly, this complex network of gravitational interactions creates a kind of cosmic feedback loop, where the motion of one object influences the motion of others, and small changes in the system can lead to larger consequences over time. While this may sound chaotic, in practice, these interactions have contributed to the overall stability of Pluto's orbit over billions of years. Another fascinating aspect of Pluto's orbit is its interaction with the solar wind. As the Sun emits streams of charged particles, these particles interact with the atmospheres of planets and dwarf planets, causing slight but gradual shifts in their trajectories. For Pluto, which resides so far from the Sun, the solar wind is much weaker than it is closer to Earth. Nevertheless, these particles still exert some influence on Pluto's atmosphere and orbit, gradually shaping its long-term behavior. This is yet another factor that scientists consider when studying Pluto's orbit and assessing its stability over vast time periods. There is also a possibility that Pluto's orbit could change as the Sun itself evolves over the coming billions of years. As the Sun ages, it will eventually enter the red giant phase, expanding significantly and potentially altering the gravitational dynamics of the solar system. This could lead to changes in the orbits of distant bodies like Pluto and Neptune. However, this scenario is still far in the future, as the Sun's red giant phase is expected to occur in approximately 5 billion years. Nevertheless, this future transformation could bring significant changes to the overall structure of the solar system, and the orbits of objects like Pluto may be altered by this process. In addition to the Sun's eventual changes, the gravitational influence of neighboring stars also has a subtle impact on the orbits of objects in our solar system. Although the closest stars are far enough away that their gravitational pull has little immediate effect, over thousands or even millions of years, a nearby star could alter the orbits of outer solar system objects like Pluto. This phenomenon, known as stellar perturbation, is not something that will affect Pluto's orbit in the short term, but it is something that could gradually reshape. Neptune, a direct collision would likely have significant consequences for Pluto, including the potential for major changes to its orbit. However, the gravitational effects of Neptune's larger mass could also influence the orbits of nearby objects, potentially sending them on new paths or even ejecting them from the solar system entirely. Such an event, though highly unlikely due to the stabilizing forces already discussed, would have far-reaching implications, disrupting the delicate balance of gravitational forces that currently govern the solar system. Although the idea of a Pluto-Neptune impact may seem dramatic, the reality is that our solar system is constantly evolving. Its planets, dwarf planets, and moons are all in a constant state of motion, influenced by gravitational interactions, the positioning of stars, and the ongoing processes that shape the evolution of our solar system. Despite Pluto's unusual orbit, it has remained stable for billions of years, and the chances of a catastrophic collision with Neptune are very low. Nevertheless, the study of such phenomena reminds us of the dynamic nature of our universe and the many forces that shape the behavior of celestial bodies.